Hello there, everybody. Here we have the mean value theorem sketched out, and we can see it on the graph here. Let me draw this line connecting A and B. And from the formula, you can see that this f of b minus f of a divided by b minus a is the slope of that line. And it's equal to the derivative of f at some point c that sits between a and b. So we could think of this curve as, oh, the trajectory of a particle. Hey, why don't we see if we can do something a little more interesting? Rather than having a and b, I'm going to do this. So let's introduce a function, a mapping. And I'm going to guess that if we're going to do that here, we better do it here. So we're going to do this and this. And that's a more general denominator. And of course, this is going to change somehow. So isn't that wonderful? A new function.
Matt, what are you doing? You're messing up my chart. You're messing up my formula. What are you doing here?
I'm trying to extend Cauchy's idea just by making this g a function of g.
Oh, I see. I see. So you're thinking of this as a little curve, maybe parameterized by something like time. So a particle moves here, and you're saying this slope is equal to a slope along there.
Yeah, we're following this idea from the mean value theorem, and we're extending it and seeing where it takes us. Well, of course, this is going to be different.
And it's not that different, though. You've got a g on the bottom here, so this is g prime at the same point c. And you mentioned Cauchy. That's his mean value theorem. So let's give it the right name. This is Cauchy Mean Value Theorem. Isn't that a nice result?
Yes. Now, how is that? We kind of know what this means already, right? So how does that go?
Well, one way to think of this is that let's look at this line here. It's a straight line. We know how to parameterize a line like this. So if you think of its slope as m, you would write this as y is equal to m times x minus x naught plus y naught. Except here, x naught is going to be this point. So this is, x naught is going to be g of a. This is a point in between, so you can sort of think of g as being a function of, say, time. So this is g of t.
Except we've got, are you confounding x and t here, or are you just calling it?
Oh, I'm calling g of t to be x.
To be x, okay.
Okay, so you think of x as a function of time.
So we have two functions of time, essentially.
So what's the other one? Y is what?
Is going to be f of t.
Exactly. Okay, so here's the x minus x naught is g of t minus g of a. My slope was this thing. Let's just call it m, because I'm lazy. And y naught, this is f of a. So this is this straight line.
That's the secant line.
And then if I take the difference between here and here, well, maybe I'll call this my little helper function like we had last time, but now it depends on t instead of x. So the top part was my f, so that's f of t. And then I subtract this whole thing. So maybe I'll write it out. F of b minus f of a. This is just some number, it doesn't depend on t. G of b minus g of a multiplied by this thing, g of t minus g of a plus f of a. That's our little helper function like in the last video.
Closed bracket.
Closed, thank you, Matt. Syntax is important.
All right, so we're in good shape. Now, what we did before is when we subtract these two at the endpoints, we're going to get 0.
Right.
So effectively, we can think of this whole thing now sitting horizontally along the axis, and what this says is that there's going to be a point on this curve where the tangent is parallel to the secant slope.
That's right. So here we have at this point, h at a is equal to 0. And why is that? Because here you get an f of a. This gives me g of a minus g of a is 0, so that doesn't matter. So I get f of a minus f of a, which is 0. And if I tried at b, I get the same thing, h of b. If I stick in here, I get f of b. Here I get a g of b minus g of a, which cancels that, giving me an f of b minus f of a. So the f of a's cancel, the f of b's cancel, so I get 0.
Great. So we're in great shape to follow the same thing we did before.
So that tells us h prime at some intermediate point is equal to 0. And can you look at this formula and differentiate it for me? Now remember, t is the variable, so we only differentiate where we see a t.
F prime of t there.
Okay. F prime of t
And minus, well, this is a that's
a constant,
a constant. So we got a constant times g prime of t.
So I'll put the g prime of t because that's the only thing we're differentiating, and I'll put the constant in front. F of b minus f of a over g of b minus g of a. So this is equal to 0. So this is equal to that. I divide through by g prime, and I get this. Oops, I forgot my little c. It's not arbitrary t, it's a special point.
Yeah,
T
c.
equal to c.
So the question is, when we put this equal to 0, we have to be a little careful. So we could write it like this, the condition, or we can, when we solve and put this equal to 0, we got this ratio is equal to that ratio. However, when you do that, you get a g prime in the denominator. So maybe we could just not go all the way down, but rewrite this as f of prime of c times this is equal to f of b minus f of a times g prime of c.
Well, you could do that too.
Yeah, and then we don't require, if we write it like this, we have to make the specification that g prime of c is not equal to 0.
That's right. So we might have a bad situation here if g prime of c was equal to 0. So for g, let's say g was something like the sine of t. You know, at some points the derivative of sine is going to be 0. So we might have a problem here. So exactly right. This is sort of the traditional form for the Cauchy mean value theorem, with the assumption that this guy is not equal to 0. Okay.
Yeah.
But otherwise, you can do it this way. And there's also this problem here, what happens if g of b is equal to g of a. So you're right, if we pull this over to the other side, we get a zero-free version.
Yeah, a zero-free version. We don't require the condition on the derivative of g that way.
Now, Matt, do you think this is just some silly mathematical generalization?
Well, let's think about this. We started out with straight lines. I mean, we see it here and in the best linear approximation near a point. And so this is really, in a sense, all straight line based. But when we're looking at functions, like sine, like Bessel functions, they have curvature in them. So we like to see how to approximate these functions. And so far we've been only dealing with straight lines. So maybe there's a way of progressing along and including curvature. So we could start with that and see what the effects are and see if there's a way of using that and then see where that carries us forward.
That's exactly right. So this tool, you can think of the mean value theorem as a tool. It's going to show us, for instance, how good a linear approximation is, and also how good a quadratic approximation is, and so on, higher in orders. And we'll see that in our next video.